Good morning and welcome to today's webinar on optimizing grid flexibility with thermal energy storage. This webinar is brought to you by the ThumbsUp project in collaboration with Best Storage, HiStore, and Echo projects. As we see more and more renewable energy sources being implemented, being developed, this helps with the energy transition, but we still face great challenges regarding their volatility. And this is where thermal energy storage has a key role to play in efficiently integrating sector coupling and maximizing the effect of renewable energy sources. Though there are solutions out there, they are still too expensive, too large, they include very polluting components, and they're not easily integrated into infrastructure or connected to the energy management systems, particularly not at a compact level. So today we're going to see how these 4 projects that are funded by the European Commission to the Horizon Europe program will bring forward solutions that hopefully will balance the grid one building at a time and change the situation. Before we get started, I would like to go over a couple of housekeeping rules. Please keep in mind, as you heard, this webinar is recorded and will be uploaded to the ThumbsUp website, thumbsupstorage.eu. Please do interact with the speakers. We are here for you. This is the point of having a webinar. So you should have a little Q&A function in the bottom. Do use that, write your questions there. And we will try to address them as they come. You will have time to ask each speaker questions specifically about their presentation at the end of each presentation, but we will also have a possibility to ask questions for the whole panel at the end. So please bear with us. I hope you think this is interesting and interactive. And once again, do not hesitate to ask questions. Last but not least, do stay in touch. These projects are just started, so a lot is yet to come. We have 4 years in front of us to bring solutions and to make these changes. So follow us on our websites, on social media, or directly on our emails. I believe you'll see the presenters' emails at the end of each presentation. So yeah, without further ado, this is the webinar, the agenda for today's webinar. First, we'll hear about the ThumbsUp project from our coordinator. Within the ThumbsUp project, we're developing 2 solutions, one short-term storage and one long-term storage. Adriana Saccovelli from the University of Birmingham will present the daily storage solutions, and Adriana Fraseca from CNR is going to present the long-term solutions. Then we will hear from our co-projects or sister projects, Echo project, presented by Sara Atana, the HiStore project, presented by Marco Calderoni, and Best Storage project by Ugo Grasset. So, having said that, Guillermo, thank you for joining us, for being here today. Could you tell us a little bit, what is the ThumbsUp project? What are we going to do? What's the purpose?
Thank you, Emilia. Well, first of all, good morning, everyone, and thank you for attending this first external webinar of our ThumbsUp project. As my colleague Emilia introduced, I am Guillermo Andrés Nieto from Veolia, España, and I am the project coordinator of the ThumbsUp project. So, first of all, what does ThumbsUp stands for? What does our acronym stand for? No? Next, please, Emilia. ThumbsUp stands for Thermal Energy Storage Solutions to optimally manage buildings and unlock their grid balancing and flexibility potential. It's a strong name, I guess, that offers a good idea about what this project will be, about the main topic, I will say, of our project. No? Next, please, Emilia. So, who are we? Who are we? The ThumbsUp project is formed by a consortium of 20 organizations from 9 different European countries, composed by small and medium enterprises, large enterprises, and research and development centers. Among these different organizations, we can find leaders in thermal energy storage research, innovative technology development, and thermal energy storage manufacturing companies. In ThumbsUp, we like to consider our slogan, balancing the grid one building at a time. to offer the main idea in just one phrase. Next, please. So just to offer a couple of words about Veolia as the project coordinator of this ThumbsUp project. Veolia is a multinational company which has presence in the 5 continents of the world, and we design and deploy solutions for water, waste, and energy management. In Veolia, we like to consider also our mission research in the world. There are some numbers about our different business fields in the presentation, just to take a look if you consider it. Next. So let's begin with this. Before talking about the different objectives of the ThumbsUp project and the different phases that will conform its development, it's interesting to firstly give a brief overview of what's the current situation and background. Why is our project necessary? Why ThumbsUp? No? Well, now more than ever, there is the necessity of reducing the emissions of the European Union buildings and the energy sector, as well as all the energy consumptions. Moreover, the achieving of the European Commission ambitious emission reduction and renewable energy sources targets up to 2030, 2050. It's true that I guess, as I guess the most part of the attendants will already know, the thermal energy storage has already proven its potential to optimize the heating and cooling demand management, but it's necessary to firstly focus on several issues, several current issues about the current technologies. No? The phase change materials are quite expensive and have some environmental issues. The current thermochemical proposals imply the use of hazardous and toxic materials, and it's also necessary to consider that the energy density and heat exchange properties of the current or the existing technologies must be increased and optimized. Finally, as we have seen during the last years, the electrified heating and cooling is beginning to be massively implemented. So there is an undoubtedly postulation of power to heat, of the technology of power to heat, as a potential storage for grid balancing. Next, please. So now that we have a bit more information about our background, what is specifically the mission of the ThumbsUp project? Well, ThumbsUp aims to overcome the limitations of the existing building integrated technologies, demonstrating the thermal energy storage at a daily and weekly level. The solutions developed within our project must be easily integrated in all the different types of European Union buildings, must increase their energy efficiency, and, as mentioned before, must exploit power to heat approaches to make the European Union buildings as grid flexibility actors. Next, please. Well, during the ThumbsUp project development, 2 innovative solutions which will receive the name of brackless and sorties and based in phase change materials and thermochemical materials respectively will be developed from the design to the implementation stage. The main aim of this of the development of these technologies will be to guarantee the thermal energy storage integration in different building areas and to target high energy density storages with a competitive cost. Next, please. Well, so how will the ThumbsUp project will be developed during the time? Well, as my colleague Emilia mentioned before, this project has just begun in January 2023 and will last 48 months until December 2026. So we are now in the 6th month of the project, totally immersed in the first phase of the ThumbsUp project, in which the mentioned technologies, the key enabling technologies, will be developed. During the second phase of the project, and after the design, after the development of the technologies of the ThumbsUp project, the technologies will be validated and demonstrated within the demonstration campaign. After the end of this second phase, the replication campaign will come. So next, please. Well, as my colleagues Adriano Sacobelli and Andrea Facica will further discuss about in their presentations about the first phase of the project, I will focus on giving a general idea about the second phase and the third phase of the ThumbsUp project. Well, after the development of both technologies of the project, the brackless and sortie solutions, The validation campaign will come in order to validate the different technologies that have been developed, and with the main aim of reaching a technology readiness level 6. Okay? This validation campaign will take place in Carti 3, a building located in Valladolid, a city here in Spain, and in which the heating and cooling systems are conformed by a geothermal water-to-water heat pump, a passive heating and cooling through boreholes, and a biomass boiler helped by a photovoltaics rooftop. Moreover, the distribution of the heating and cooling system, it's actually a radiant floor, heating and cooling, and air handling units. In this validation campaign in the Carti 3 building, both technologies of the project will be validated, the Sortis and Frackless ones, with 20 kilowatt hours for heating and cooling in the Sortis solutions, and with 14 kilowatt hours for heating and domestic hot water in a centralized level for Frackless solutions, and 9 kilowatt hours for heating and domestic hot water in a floor level for Frackless also solutions. So after the end of this validation campaign, next slide, please. The demonstration campaign will take place in 3 different pilots located in two of them in Spain and the third one in Sweden, in order to reach a technology readiness level 7. The first pilot of this demonstration campaign is a single family building, which is located in Segovia, Spain. And thank you, Emilia. And in which the heating and cooling system is conformed by an air-to-water heat pump project with a projected photovoltaic rooftop that will be installed during this first year of project development. The distribution is done by a radiant floor of heating and cooling. In this pilot, the demonstration of the both technologies, Sortis Frackless, also will take place with 100 kilowatt hour for heating and cooling at the Frackless, at the Sortis solution, and for 9 kilowatt hours for heating and domestic hot water, and another 9 kilowatt hours for cooling purposes for Frackless solutions. Next slide, please. The second pilot of this demonstration campaign is a multifamily building composed by apartments and a nursing home, which is located also here in Valladolid, Spain, with a heating and cooling system conformed by air-to-water heat pumps, a natural gas backup boiler, and with a projected photovoltaics rooftop that will be also installed during this first year of project development. The distribution is done by a radiant floor heating and cooling. And in this building, the Frackless solutions will be demonstrated in a single flat level with 4 modular heating and domestic hot water purpose Frackless solutions of 9 kilowatt hour each, and in a centralized level with 7 modules of 14 kilowatt hours for cooling purposes. Next slide, please. Finally, the third pilot of the ThumbsUp project is located in Gothenburg, Sweden. And it's a multifamily building conformed by several apartments with a district heating connection and with air-to-water heat pumps, borehole heat exchangers, and also with a photovoltaics rooftop as a help to the generation, to the energy generation. The distribution is done by a radiant floor, and in this building, the demonstration action will be of the Frackless technologies of the project in a single flat level with 5 modules of 9 kilowatt hours for heating and domestic hot water, and in a centralized level with 4 modules of 14 kilowatt hours for heating and domestic hot water. So next slide, please. With this, the second phase of the project will be finalized, and the third phase regarding the replication campaign will come. The main aim of this replication campaign will be to simulate the integration of the both technologies of the project for heating and domestic hot water in order to study the impact at district heating network and electric grid level, and also to study the impact in terms of reduction of the district heating operating temperatures and consequent increase in the renewable energy sources penetration. 5 replication sites will take place in the ThumbsUp during the ThumbsUp project, and by now 2 of them has been already selected in Netherlands and Italy. So next slide, please. And in order to finish this first overview of the ThumbsUp project, we have been discussing about the different phases of the ThumbsUp, but let's talk about the expected outcomes, some specific numbers of our project. What are expected to be the most relevant impact of ThumbsUp? Well, with the ThumbsUp technologies, we aim to reach high energy densities up to 65 kilowatt hours per meter cubic and 120 kilowatts hour per meter cubic for frackless and sorties technologies, respectively. These technologies must be presented in a modular situation with different scales, providing low temperature distributions for heating and cooling, and being easily coupled to heat pumps. These technologies will be mainly characterized by their compactness, their reliability, and their cost competitiveness and installation flexibility, as these technologies will be all in all with a capex of 140 euros per kilowatt hour and 200 euros per kilowatt hour for the two technologies developed within the project. With this development, we will reach a peak shifting of the renewable energy sources with a potential exchange with the district heating network and other buildings. And all in all, and as a summary, we expect by 2030 to have an expected outcome with the replication of the ThumbsUp solutions in at least 1,000 buildings across Europe, and to trigger an investment of at least 200 million euros. So, well, I hope all of this makes a general idea of the ThumbsUp project development, and I hope I could share with you a bit of our sensation of this exciting project that will last 4 years. And well, just stay tuned on our social media in order to receive the feedback from the nice work of our colleagues of the Johannesburg Science Park in terms of communication and dissemination activities. Thank you for attending.
Thank you very much for that. I don't think I've ever heard you speak that quickly. That was really impressive. Yeah, thorough. So thank you for that overview. I have a question here. So I just want to remind the audience, do not hesitate to use the Q&A function at the bottom. I have a question from Javier Castro. Could you please repeat what TES and fractless stand for? Would it help if I show the slide?
No problem from my side. I don't know if it's about the meaning of the sorties and fractless names, but as my colleagues Adriano and Andrea will further present during their following presentations, as Adriano will present the fractless solutions, and my colleague Andrea will present the shortest ones. The fractless solutions are solutions based on phase change materials, and the sortie solutions are solutions developed within the ThumbsUp project based on thermochemical materials. So the name basically comes from two different parts, I will say, because frac comes for fractal, I will say, but Adriano will further specify during his presentation, and TES, the thermal energy storage that we have been discussing during this general presentation. And in shortest, it happens exactly the same, I will say, because it's among sort that comes for sorption technologies, sorption, and the other part, thermal energy storage, as it happens with also the other technology of the ThumbsUp.
Great, thank you. So that leads us to, let's hear a little bit more about this TES from Adriano. Welcome, you're joining us from the University of Birmingham, where you're a professor. So please, could you tell us a little bit more about the solution that the ThumbsUp project will be developing during the next 4 years, or 3.5 years?
Sure, thank you, Emilia. I'm gonna share my screen, and you can see my screen. So my pleasure to be here to present the fractless solution, which indeed stands for fractal latent heat energy storage solution, part of the two technologies developed in ThumbsUp. So I'm Adriano Sciocovelli from University of Birmingham. We are, let's say, leading the work on the latent heat solution together with many other of the colleagues and partners in this project. So I have essentially three objectives with this presentation. I want to give you a rationale about the solution that we are proposing, particularly in the context of ThumbsUp, give you some targets and objectives, so what we are aiming to develop specifically, and ultimately to give you a little bit of insight from technical standpoints about the ongoing activities and what has been done so far, based also on the, let's say, prior work that obviously supported the preparation of the overall concept and the technological proposal. So I would like to start perhaps by kind of giving a quick rationale of how we look at the short duration or the daily thermal energy storage solution in the context of this project. So we are looking at let's say, through three different angles. One, we aim for, with short duration storage, to help basically improving the efficiency of existing heating and cooling delivery systems in buildings by basically rectifying problems like oversizing, misbalance between supply and return temperature in the existing buildings. But obviously, as Guillermo said, we are looking at longer, let's say, timeframes. So we want to look at how the TES short duration maximize the use of renewables, both on sites, both electricity and heating, and obviously allows some energy flexibility through a shift in thermal demand and electrical demand over time. So that's the main role of the short duration TES system developing this project and the fractal solution. Obviously, probably I'm preaching a little bit to the choir here, so I'm not going to spend too much time in the working principle, but we are looking obviously at a PCM-based, so a latent heat-based system where we exploit the solidification and melting of bespoke phase change material that is, or a class of phase change material that are developed in the project. Perhaps one thing that I want to emphasize is that we are looking at a solution that can interface both with the heating and cooling side of the buildings, but also with the renewable electricity through heat conversion or power to heat conversion. And on the discharge side, delivery of heat for space heating and let's say hot water purposes, and in the instance of the device or the TES system developed for cooling application for cooling, environmental cooling. So obviously this is, let's say, well known. It's the basic fundamental working principles. I want to emphasize before I dive into the technical details that there are plenty of other challenges, not just obviously the material scale, but at the interfaces and components that allows to exploit the potential of the material. So quite a lot of the fractal solution and the work is focused also at the component level and overall system and device scale, so that ultimately we can develop a system that has efficiency across all the, let's say, intermediate, let's say, storage and conversion steps that occurs in a thermal energy storage system. So interfaces for charging and discharging, component for charging and discharging, and obviously the material itself. So let me therefore give you, let me move to a little bit more technical details. So part of the project and the consortium, an important role is played by a technology developer that works within the consortium, TES from Italy, and let's say located in north part of Italy in Turin, which is, let's say, in a way the starting platform of the solution that we developed. So what you see here, it's a 3D representation, 3D model of the existing, one of their existing products that forms in part the starting point. But we are looking obviously at a solution that can be integrated, as I mentioned, with some extra components and parts that allows these flexibility in supply and delivering heat and cooling in the buildings, as well as flexibility provided toward the networks that connects to the building where the storage is, electrical network, and potentially also district heating network. So therefore, we're looking at conversion, power to heat, direct to power to heat, integration with heat pumps and local renewables to obviously supply, let's say, heating and cooling, or integration with the heating and cooling distribution system, as well as the domestic hot water system in the building itself. So I would like to perhaps emphasize that obviously is a, let's say, collective effort through a number of let's say, partners with different specialized expertise that are all integrated together in the work package dedicated to this part of this technology. I just mentioned here at the bottom, let's say, task leaders in the work package working, developing the the TES system, the short duration. So at a material level, we develop, optimize a bio-based PCM. At a component level, some novel heat exchanger configurations, from which, let's say, the name stands for, with some, let's say, non-conventional geometries that I will show you in a second. Then at control level, obviously, the possibility to define and develop new control strategies is quite important. TES needs to be controlled and operated in a smart way to maximize its potential. Here we have the support of the Cardiff system and overall prototyping and manufacturing, as I mentioned. TES is part of the consortium as also key, let's say, beneficiary of the work, so that we envision and we have the ambition that the solution that is developed and proposed at the end of the project becomes ultimately nearly a commercial product that TES can integrate in their portfolio of offer. From target perspective, we are looking at reducing capex for materials by developing a bio-based PCM that uses basically waste from food industry, and through a catalytic process this waste is converted in PCM that ultimately belongs to the class of fatty acids type of PCM. Component level, use existing manufacturing techniques but apply to develop new geometries or new heat exchanger that are part of the TES system. And by doing so, ultimately maximizing the storage capacity at system level, at component level. So targets, let's say, that are around 60 kilowatt-hour per cubic meter. Reduce the capex, again, at system level at approximately 140 euro per kilowatt-hour, and have a system that is modular, so that we can obviously tune the capacity depending on the application of the vehicle at the end. So from bio-based point of view, bio-based PCM point of view, here just one slide to give you a glimpse about the synthesis rules that University of Yale in this case is developing, starting from their prior knowledge in the process. In a nutshell, we are looking at starting from not edible animal fat and obtain phase change materials that are, let's say, again, with characteristics that are very similar to those of fatty acids. So melting temperature typically in the range between 40 and 60, through a process that comprises a number of steps that are basically epoxidation, then cleavage hydrolysis of the waste, so that is turned into saturated fatty acids through a biocatalyst, and then finally crystallization and eventually esterification process to essentially put together the right PCM with the right melting temperature, which we target between 40 and 60 degrees. And we're working with the current, let's say, player in the manufacturing of PCM to look at the upscaling of these fabrication route also in the context of the project. At component scale, I want to emphasize what basically is this idea of a fractal heat exchanger or fractal components. So we are looking at an arrangement that is modular, is a plate type heat exchanger embedded in the module, but also with the electric heating elements that allows direct power to heat conversion. Here we are starting with obviously the experience of TES and our methodologies and methods at the University of Birmingham dedicated to design, configure, optimize heat exchanger while including and retaining constraints of manufacturability. It's essential that we develop solutions that are easily to manufacture for cost point of view, but also for scalability, so that we can capture a very extensive market by having volumes of manufacturers that are interested also for heat exchanger manufacturer. So in that sense, we are looking, as I said, at plate type heat exchangers configuration that are these, let's say, placed in a parallel arrangement and in direct contact with the phase change materials. And here we look at, let's say, develop the flow path configuration driven by, let's say, numerical techniques and methods that we developed at the University of Birmingham, which we broadly call topological optimization methods. And that leads to geometries and configuration we are confident are more so high performance, but still manufacturable at a reasonable cost. And we are in contact with the manufacturers that will ultimately produce these components for the final demonstration in the project. I'm going to close here, spend 30 seconds just to emphasize the ongoing activities and what's coming up in the next few months. Obviously, the synthesis in the PCM is an important part and is carry on in the next few months, but taking into account also potential scaling up of the manufacturing to make sure that we develop the right PCM with the capability to be fabricated at scale in principle. and then to test and develop this heat exchanger and overall TES module, initially at lab scale, both in our facilities at Birmingham as well as in ITES facilities, to do pre-validation that allows us to be confident on the design and performances before we move to the validation in the pilots in Cardiff and in the other demo sites of the project. I'll stop here. I hope to receive any interesting and stimulating questions, and I'm happy to answer those. Emilia, back to you.
Thank you very much. That was a very enlightening presentation. If you want to stop sharing so we can see you, it's always nice to see on the big screen. We do have two questions. The first one is, what is the maximum storage duration for the solution?
Yeah, so we start, so we target 3 hours storage duration as minimum storage duration. That's a target of the, actually of the call for proposals, and a charging rate of 3 kilowatt. And we are looking at intraday solutions. This means that essentially up to 24 hours of storage before, let's say, self-discharge effects kicks in, and before obviously also economical effect kicks in, where if the duration is too long, obviously we have not sufficient number of cycles, and therefore also lower revenue stream. So 3 hours to 24 hours as a ballpark figure.
Okay, great, thank you. I have also a question from Varun. Is it feasible to run the new developed PCM materials with currently existing components, or will new components be needed for newer materials?
Yeah, thanks. I'll perhaps read through the question. When I hear components, I think about, let's say, the components that interacts with the PCM. If that's not correct, just please let me know. But in that instance, let's say the PCM in this specific project, in these specific activities, the target and the final characteristics of the PCMs are relatively known. They belong to a class of a very well-known existing PCM, let's say fatty acid PCMs. What we are doing differently is that we start from waste, and we have a different route to produce these PCMs. So we have a kind of more circular economy approach, because we use waste, first of all, and we use a more sustainable, let's say, route to produce PCMs with characteristics that are relatively well known. So in that case, the interaction with components is not expected to be different from the, let's say, interaction that we already know. In that sense, that's why also we have heat exchangers and components that need some optimization, need some refining, but we do not expect a massive difference in behavior and interaction between the PCM and the components.
Great, thank you. We have time for one more question here from Daniel. You mentioned starting discharging power of 3 kilowatt. Will it be average? Will it be the average discharging power?
Yeah, good question. So I think, yeah, we will at least consider this as a sort of average discharge power during the discharge process, factoring in obviously the unavoidable behavior of probably initial spike in the discharge during the very initial phase, then a relatively range of time where the discharge is relatively constant, then a fade off of the discharge. So let's say we target obviously this main central stage or central phase of discharge, the one that delivers 3 kilowatt hour, taking into account that we have something probably slightly higher at the beginning and slightly lower at the end. So overall, on average, would be a 3 kilowatt as a charge and discharge power.
And for those of us who are newer to these concepts, is that considered very high or rather average or rather low in terms of what's the available technologies today?
So in terms of, let's say, charge and discharge power, we are looking at, let's say, overall a modular concept that allows to also build not only the capacity, but also the discharge power in, let's say, series or in parallel. So ultimately, we can meet with the discharge power the requested discharge power by the heating and cooling system in the building. So obviously, let's say we take an example, one of the one of the Veolia demo sites, single family house, will have a relatively low discharge power, and there we go with the smaller components that has a certain discharge power that meets the required heat rate from the building. while the other one, the multifamily building, that's why you've seen in the previous presentation with Guillermo that we have a number of modules that allows to meet a higher discharge power, higher storage capacity, because obviously the building is larger and therefore needs more heat at each instant of time and more energy overall. So it's modular and it's tuned to the needs of the local building, essentially. The 3 kilowatt, let's say, in charge and discharge, in a way, comes from thinking around the typical charge rate and discharge rate of heat supply technologies, like heat pumps that are available in the market.
Great, thank you. I think, Sebastian, think you wrote a question. Unfortunately, or fortunately, we need to go on to the second storage solution, but I will keep this question for the panel discussion at the end. Having said that, Andrea, I welcome you to turn on your camera. Thank you. And so you are working for the Italian CNR, and you're going to be working on the long duration storage test solution. Could you please tell us a little bit more about this?
Yeah, good morning, Emilia. Thank you. And thank you all the participants to this webinar. It's a pleasure for me to present here the long-term duration storage of the ThumbsUp project. So, yes, as Emilia anticipated, I'm from the National Council of Research from Italy, working with storage technology since many years. Next, please. So, I mean, the agenda of my presentation is quite similar to what Adriano was showing before. So, I'll skip the outline and then diving directly inside the technology concept. I apologize already from the beginning if some of the concepts I'm sharing here are already well known, but I know that usually thermochemical storage is not the most common technology on the market, and maybe it's helpful for you to know which are the differences compared, for example, to the latter technology that Adriano was presenting before. So the main difference of any thermochemical storage is that we are not only exploring the thermal swing during charging and discharging, but we are mainly relying on reversible reaction. This reaction can be either chemical or physical reaction, but in general it happens between two components. One component here is the A, which is the let's say the phase where the two systems are together, while this component C is the volatile component, which is basically the working fluid. And if we shift to the next slide, the next step actually, what happens is that the heat storage charging reaction is an endothermic reaction. So, which means that we start from the two components together in the phase A. We provide heat at high temperature, and we separate the two basic components B and C. And if we move to the next, if we keep these two components B and C separated, so we don't allow to recombine them, we keep the energy stored for a long time. That's why we can get the long-term energy storage under these conditions. And if we skip to the next one, yeah, when we let the B and C components recombine, then the exothermic reaction is happening again. So we are again getting the component A and getting back the heat that we were storing before. As you can see on the top of this slide, basically the component A and B can be either liquid or solid. And in case of ThumbsUp, as you will see, we are relying on solid sorption. So we are basically exploiting the surface of the material to store this volatile compound, and we are also exploiting a thermochemical reaction in a salt. So the next one. Very briefly, these are the phases in a, let's say, super lumped approach. During charging phase, we provide it, we desorb this water vapor, which is our working fluid in this case, and we condense this water vapor, basically rejecting the heat to the ambient. Next one. Then we keep the heat stored as long as these two components are kept separated. And then next one, we have the capability of again evaporating the liquid into the vapor phase and let the material absorbing this vapor phase and releasing it to the user. So this is overall the concept of absorption storage. And if we move to the next slide, this is how we conceive the ThumbsUp Sortis technology integrated inside an overall energy system. So here, basically, we rely on a power to heat converter because mostly, as requested by the call, the system is focused on, let's say, exploiting the renewable from the grid. We charge our absorption storage, and then we, of course, can provide both heating during winter season and cooling, because as you have seen before, we are connecting our absorption device to an external source. So during charging is, let's say, the ambient, because we need to release and condense the water vapor, basically. While during this charging, we evaporate to take out energy from the ambient and provide the water vapor to the absorption storage. So we can exploit the process in both cases, and we can provide heating during winter and cooling during summer. So the system is able to work in both cases. And what is, let's say, new for this project is that differently from what was done in the past, we are not aiming at having seasonal storage. So we are not shifting solar energy from summer to winter, but we are working in weekly storage concept. So we are charging and keeping the system, let's say, operating for 1 week, 2 weeks, up to 4 weeks as the call was requesting. So we also can achieve a system that is, let's say, more compact than other cases in the past, let's say, developed in previous projects. Next one, please. Of course, we are facing many challenges and many innovations during the project. As I said, the aim is to develop, manufacture, and test absorption storage, which has a long duration, weekly in this case, and able to provide both heating and cooling. And here we are working at material level, optimizing composite sorbents. So from cost, energy density, stability, and scalability point of view. We are working at component level in order to make the system more efficient, especially more cost effective. We are aiming at profiting of HVAC existing heat exchanger to modify them for the specific Sortis concept. We are working at control level, mainly to develop new ways to monitor these technologies, which is something quite new in the literature, and also to let the system being better operated thanks to this monitoring phase. And at system level, of course, designing a system which can be easily installed and integrated in a typical heating and cooling system, considering that heat pumping are considered as the main heating and cooling technology to be connected to the Sortis. Next one, please. And here are some of the targets that we have in the project. I will focus mostly on the energy storage density. Of course, generally the energy storage density is reducing from material level down to system level because of the use of the other components like vessels, heat exchanger, that are, of course, reducing the overall energy storage density. Our aim is to reach up to 120 kilowatt-hour per cubic meter when the system is integrated inside the building, and also considering the heat losses that we face when we have weekly operation. And then we also target reduction of the cost of the material, the composite sorbent, down to maximum 5 euros per kilogram, and in general, reaching capital cost of the technology lower than 200 euros per kilowatt-hour of storage density. And what is also relevant for, at least for our application, is that we conceive it as a system that must be integrated with heat pump. So in principle, this should also enhance the seasonal efficiency of the heat pump. Here, we expect the seasonal COP up to 6. Next one, please. Briefly inside the many innovations, as I said, the material level, we are targeting the development of composite sorbent. Basically, a composite sorbent is a matrix, a porous matrix where a salt, which is the active phase, is embedded. In this way, we can enhance the thermal energy storage. This is not a new concept. It was developed many years ago by some colleagues from Borisov Institute of Catalysis in Russia, but here we are trying to optimize it in order to not only improve the energy storage density, but also maximize the mass transfer efficiency. So we are also working on the integration of additives that can increase the heat transfer efficiency and the mass transfer efficiency inside the reactor, and also acting as a trap of possible salt leakages out of the pores of the matrix, so to enhance the stability. And what is also relevant is that this material is not commercially available, so we have a company from Greece supporting us to also scale up the manufacturing process up to, let's say, tons of production per week in order to be able to manufacture enough material for the final prototypes. Next one. While, as I said, for the components level, our idea is to try to reduce the cost by making use of commercially available heat exchanger derived from the HVAC industry. Of course, here the idea is that we need to optimize these heat exchangers, so we'll try somehow to modify them to keep the efficiency of the system, but reducing the overall capital cost. What is also relevant is that we have inside the consortium as a main technology manufacturer for the sorption technology, the company from Germany, which is exactly called Sorption Technologies, and we are exploiting their new patented solution for sorption devices, which is starting from the well-known adsorption cooling technology, but in this case, trying to, let's say, maximize the heat and mass transfer efficiency by exploiting the refrigerant, so the water in the liquid phase instead of the water vapor phase. And of course, in the end, we need to equip the system with an integrated power to heat converter in order to be able to exploit the renewables from the grid. Next one. Just very few examples, let's say, updates regarding the ongoing activities. Of course, the project just started 6 months ago, so we just have some brief results. Here, some of the samples that we started preparing out of dry impregnation using silica gel and calcium chloride as a composite storage. Here you see basically the process, which is a typical dry impregnation process. And here are some of the samples that we got so far with different amount of salt loaded. Next one. What we are doing right now is to compare different ways to manufacture the material. Of course, then there is also an ongoing activities on the optimization of the material itself. And as you can see here, basically using dry and wet impregnation, that are two quite common methods in literature. We get on the left-hand side, you see the equilibrium curve, so the storage capacity, which is more or less comparable. But what we highlighted so far is that using the wet impregnation method, which is the one on the right-hand side, the material looks more stable in the sense that there is less aggregation of the particles. So we are now trying to investigate why we got this result and if it is also applicable to other matrices and other salts to optimize the material and define the optimal one by the mid of next year. Next one, please. While here, just briefly, the architecture of the reactor we are developing so far, we are trying to shift to cylindrical vessel instead of prismatic one, also for mechanical stability issues. And we are now investigating possible integration of heat exchangers inside the reactor. We are in contact with some heat exchanger providers to check the most suitable ones and which parameters can be modified starting from the commercial products. Next one. And finally, just a recap of the future activities. Of course, we will continue synthesizing other candidates in terms of salts and matrix and additives. We are working already on the scaling up phase to understand how to optimize the manufacturing in a large scale. And we'll move on with testing the first lab scale thermal energy storage, also working in collaboration with SET from Greece to optimize through CFD the adsorber heat exchanger design. And finally, the technology will be tested in a single module of 20 kWh before being validated in the demo site that Guillermo was presenting before. Thank you.
Thank you very, very much. That was very enlightening as well. I think it's great to have these webinars because you learn a lot about the projects you're working on. So you said you're already using things that are available. What do you think will be the greatest change that the work you're doing through the ThumbsUp project will bring? What will be the most drastic game changer?
You mean at material level or in general?
Material level.
Okay, at material level, basically the idea is, yes, to profit of the experience we got in previous projects, but trying to, first of all, reduce the cost, because this is one of the main barriers for these materials, because most of the time we need to use very expensive salts to enhance the performance. So the idea is to investigate, let's say, cheaper salts on the market. And the second big point is how to scale it up, because usually the manufacturing is done in the lab, so a few kilograms per day, for example. And this is, of course, not suitable for a large deployment of the technology. Of course, in the project, we are going to validate 2 prototypes in the demo site, so we can even rely on our capabilities in the lab. But the idea is that since we are reaching TRL 7, by the end of the project, we should also provide to the technology manufacturers like Solution Technologies a way to manufacture the material either directly by themselves in their facility, or let's say asking for to companies dealing with chemicals and stuff like that to develop a manufacturing plant for this kind of technology. So the idea is, of course, to reach this stage is quite challenging because we are really starting from the lab. But I have to say that this was also one of the requests of the call. So working also at material level, even if we are already in a higher TRL call.
Thank you. I would like to take this opportunity to ask Sebastian's question. And I would like to ask Adriano and Guillermo to turn on your cameras, take a couple of minutes to discuss between the representatives of the ThumbsUp project. Sebastian has a very interesting question here. What is the time frame to get the commercialization of these systems? Will they be able to come to the marketplace? When do you see that? And I would like to ask that, what is the process you see for that commercialization?
Well, actually, to answer this question really with question, it's necessary to know a bit more about how these technologies will act in the framework of in the European framework, I would say. We have a dedicated task in the replication activities of the project, in which the social and the market acceptance will be studied. Now, this is one of the most important parameters that must be considered in order to talk about or to answer, to properly answer when will this be ready to be introduced into the market, no? Because it's important to consider also that we need to properly define a business plan, to properly define several business models to apply these technologies into the European framework. And just to reach a technology readiness level 9, that will be the one in which the actual systems are ready to be applied in the European environment, I would say. But yeah, the project will end by 2026. So as I mentioned in the general presentation, we have some foresights of the replication of the technologies by 2030. And if all goes well, I hope so, we can reach this number with a proper market study and a social acceptance study. Yeah.
Do you see any challenges from the material technical side, Andrea and Adriano, to reach this level? Because 4 years could be a very long time, but it could also be very, very short. What do you see are the challenges for each of the technologies for this commercialization? Because do we want to bring both, or will we eventually have to focus on one?
I can give it a go. I would say that yes, in general, my perspective, my view is it's about three main pillars. Kind of the physics of the problem. So does the technology does what's supposed to do, and does it, let's say, at a relatively high level of performance? The economics of the problem. So does it do it economically, and the regulatory aspects. So obviously, let's say from our specific perspective, first and second one are probably the main aspect that the project will probably try to resolve. So the behavior and the physics of the problem, so the technology performances and the costs. So from material point of view, going back to your specific question, in our specific case, we have quite clear target in terms of material. We know that materials at the end of, let's say, synthesis process do exist, and they already exist, but they are fabricated in a not sustainable way at a relatively high cost, and they will be probably phased out given the general decarbonization, also the manufacturing sector. So the main challenge from a material perspective in our project is to have this, let's say, synthesis process that is reliable and is scalable. So does it lead to the, let's say, material that we want in terms of characteristics and can be done at large scales? If I have to rank the two of them, let's say first one, there is relatively good evidence with the consortium and other partners that we can get those performance and those characteristics. The scale up is a quite challenging part, and it's I think the, let's say, the one risk, if you want to put it in that way, that either speeds up or hinders the let's say, commercial ability. But luckily enough, let's say we have obviously on board the project a PCM manufacturer that has experience in this space and a few alternatives to have scalability together with performances.
Thank you. Andrea, is there anything you'd like to add?
Yeah, I mean, from absorption technology point of view, in principle, the cooling technology based on this process is already on the market. So somehow thermal energy storage is an extension of the technology, which has, let's say, big challenges because in general, in the end, the cost of the system is always quite higher compared to, for example, a sensible storage or latent storage. So provided that we are able to reach the performance that we are targeting since the beginning of the project, what is also important is that then the market, the end user needs to see the need for this kind of technology. Because usually if you go on the market, you just look for typical tank or sensible storage and using it as a daily storage. While here, this system becomes competitive only when, from the market perspective, we need to have a long-term storage in our buildings, which right now is not the case for, probably for most of the applications. So, of course, we, especially us as R&D centers and also SMEs, are focusing primarily in demonstrating that this technology is working. But then, and of course, this I'm not sure will be in our hands. We need to promote this in a way that the end user feels the need of having this technology at their premise, which is probably the biggest challenge in the end. And here we rely a lot on Veolia because they are a big company dealing with these technologies. And if they are able to show that this technology, also to their customers, this technology can provide them the flexibility and, of course, an efficiency and economic return, then we will be able to enter the market a few years after the end of the project if we reach the TRL7 that we are targeting.
Thank you. I wonder if our sister projects from the TES cluster have the same thoughts. How are their approaches? Because we've seen one approach to these thermal energy storage solutions. So now I want to hear, let's see what other European projects are developing. With that, I would like to welcome Sara Atana, who's Communication Manager at European Funding Development for Warrant Hub. So thank you for taking the time and joining us today to tell us a little bit more about the ECHO project, which stands for Efficient Compact Modular Thermal Energy Storage Systems.
Hi.
Would you like to take over the screen and share your screen?
Yeah, if I can, I will share my screen.
Please do.
Okay. Many thanks, Emilia. Many thanks for inviting us, for presenting our project. This is one of the first time we present to the public our HICO project. My name is Saratana. I work for the dissemination and communication actions of ECO project. And today I will present the project on the behalf of the project coordinator, Laura Fedele, that unfortunately cannot be here with us today. With me today is also one of his colleagues, Giovanni Ferrarini, that he's here to answer your questions. And just let's see very shortly what the project is about. So HICO project, HICO stands for Efficient Compact Modular Thermal Energy Storage System. The project, like the other one in the same call, has started the 1st January of this year with the total contribution of more than 8 million euros. You can find here all the details of our project and of course our project website, where you can find all the information related to the project, and our social account that I invite you all to follow. Here you can see our consortium. The partners, the consortium is composed by 17 partners and 2 affiliated entities. One is my company, Warren Tab, that is a consultancy company that helps support other companies and research centers to apply to EU funding projects. And inside the projects, we work as dissemination managers and project managers. Our entities, our companies and research centers comes from 7 different EU and extra EU countries. As you can see here, all the logos and all the name of our participants. But just start presenting the project with a little bit of background of why this project was founded. As Guillermo said also before, energy storage is one of the key factors to reach EU aims to be climate neutral, but by 2050 with a net zero greenhouse gas emissions economy. But also global energy demand will rise due to the economic development and the population increase. The ambition target to reduce these emissions is pushing towards a severe change in the employed energy system through decarbonization and with the transition to clean energy sources and the improvement of the energy efficiency. So what we need is to develop a flexible energy system just to manage the increasingly nature of renewable energy sources, as well as grid electricity production and demand. This is to find a solution in the potentialities of the thermal energy storage system that will be able to provide electricity load shifting by means of energy conversion and storage. And this is why ECO has been founded. ECO aims to develop solutions that will be flexible and adaptable to different end user requests in terms of charging and discharging power, dimension, and types of energy sources. So our goal is to develop and demonstrate a novel modular, compact, high performance and plug and play thermal energy storage solutions for heating, cooling, and domestic hot water production. So the main feature will be, of course, the ability to provide electricity load shifting with meaningful peak shaving of the thermal and electric load demands. And to do this, the project will provide a key tool for thermal energy storage in the context of sector coupling and provisional of flexibility and demand. So what does the system, the ecosystem will be? This system will be adaptable to different energetic scenarios, will be modular, and also feasible to be charged directly by means of an internal heat pump, exploiting the electricity overproduction from the grid or directly connected to renewable energy sources installed in the building. You can find here our methodology. So we will start, of course, with the screening of the energy scenarios and the parameterization of TES, thermal energy solution. We will select materials for storage and design system, optimization and integration. Then at the third step, there will be the prototype and testing. In fact, the ecosystem will be demonstrated in 3 demo sites in Italy, in Serbia, and in Belgium. And then we will do a simulation of the thermal energy storage system used at city level with this tool that will be called EcoTSS. These are the main impacts that the project will achieve. So replicability, of course, social economic impacts, environment, because EcoTS solutions will contribute to the mitigation of climate change. We hope also in a market transformation. So we will do all the necessary actions to build a social acceptance of the new energy technologies, and we will try to increase participation of consumers in energy markets and also policy, because eco results can help the energy sector in informing citizen and policy bodies to drive to positive implication in the use of these kind of systems. But I would like to show you this short video we have developed some months ago. This video underline better than me, of course, all the purposes, all the main aim of the project. So I try to share it again, sorry, because I just have to include the sound, okay. And now I start playing the video and I hope you can join it.
The European Union aims to reach a net zero greenhouse gases, GHGs emissions economy by 2050. Energy storage is a key factor in this green transition. The actual market of energy storage systems is mainly focused on electricity storage solutions, with consequences in terms of availability, costs, and environmental impact. ECHO is a European project with the aim to develop an alternative system exploiting thermal energy storage (TES) solutions. ECHO will be compact, flexible, modular, plug-and-play, sustainable, and digitally controlled. TES solutions are based on the optimization of thermochemical materials, TCMs, combined with phase change materials, PCMs, for space heating and cooling, hot tap water production, and ice storage. ECHO will be feasible to be charged in different ways, exploiting the electricity overproduction from the grid, directly connecting to renewable energy sources installed in the building. Electrical energy can be converted in thermal energy by means of a heat pump. ECHO system will be designed for different energetic scenarios and different scales, from small apartments to larger buildings. The project results will be validated in a first lab prototype and then in 3 different demo sites in Italy, Serbia, and Belgium. Meanwhile, in the cities of Bilbao and Valencia, the operation of widely diffused TES systems will be simulated at city level. Impact and potentialities of ECHO technologies at a large scale will be tested with an agent-based transaction simulation system, EcoTSS, to define how individual small-scale systems could operate synchronically in different markets. ECHO will demonstrate the sustainability of TES solutions in terms of abatement of greenhouse gases emissions, energy peak load shaving, and costs avoidance in the residential sector. This project will even contribute to the awareness of EU citizens and policy bodies about the positive implications of TES, and to investigate and solve constraints for the penetration of such technologies on the mid to long term.
Okay, I hope you the video and also the presentation. Thanks for your attention, and if you have any question, please you can ask or write in the chat.
Exactly, thank you for that prompt. It was a very interesting video, though I'm not sure they did a better job at explaining it than you did. It always helps with an animation. But looking at the time, we will wait for keep the questions towards the end so we can have a little bit of discussion with the whole panel. So I'd like to take this opportunity to ask Marco Calderoni, who is Senior Project and Innovation Manager Expert in the field of renewable thermal energy and European planning at R2M solution. Marco, would you like to turn on your camera and tell us a little bit more about the HyStore project?
Yes, of course, Emilia. Thank you for the introduction. Can you confirm you can see my presentation in full screen mode and my face?
Yes.
That's great. Okay, yes, indeed, I'm going to present the HyStore project. This is, let's say, a general presentation I'll be doing. In case of very technical questions, my colleague Kian Wang, who is also connected, can help me answering. I am employed at R2M Solution. We are responsible for communication, dissemination, and exploitation activities. And as said, today I will be giving a general presentation of this project, which will last 4 years with 18 partners and is coordinated by David Veretz from ARC Barcelona. This is, in short, the list of partners, and I would just like to point out that HyStore, as probably other projects presented today, is part of the Bridge network, and we're very much interested on everything, but particularly on the business model work package, because we have quite an extensive business model activity under HyStore. Now, the main scope of the project is to develop and validate 4 different solutions in terms of thermal energy storage concepts, 3 based on PCM, 1 based on TCM, so things we have been hearing about today a lot. Those solutions are expected to cover all the 3 typical needs or energy demands in residential and tertiary sectors, which are heating, cooling, and the domestic hot water, of course. On top of that, the project has an extensive part dealing with sector coupling. And this will be let's say, the focus of this short presentation today. So in principle, it's about developing a smart aggregator connected to an open source platform, which will be able to, talk to the grid and aggregate demands and offer flexibility services up to perhaps frequency control. Now, this is, let's say, the first guess of a general picture of how the concept will look like. Probably still needs some adaptation, but in short, this is the core of the ICT part of the project, a smart aggregator connecting, let's say, connected to many storage, to many sensors, IoT sensors and devices connected to the grid in a way that it can, get signals from it. On the other hand, get signals from local renewable energy sources, state of charge of storages, energy demand of the building, and decide whether it makes sense to operate the heat pumps or even our storages via the grid or via locally available electricity, etc. Now, why, and this is one of the main, let's say, interesting parts of the project. This direct arrow from the grid to one of the thermal storages probably should go for the smart aggregator. As said, we will improve the picture, because one of the technologies is based on TCM, so sorption storage, charged via radio frequency. That means we're using actually electricity to charge it. And then the storage becomes a direct asset for sector coupling. This picture summarizes all the main innovations in the project. So we have a so-called all-in-one PCM storage. So this is a PCM plus heat pump meant to provide heating, cooling, and domestic hot water. We have a low temperature PCM storage meant for heating, cooling, not for hot water. We have a PCM storage designed only for heating. All the three are storing at the daily basis. And then we have the TCM storage I was talking about before. And this is supposed to be a long-term, medium-term storage up to 4 weeks. So on the left-hand side, we have the hardware part. And on the right-hand side, we have the more ICT-rated parts, which I shortly reported about, but I'll be going more into the detail later. And the objectives are very similar to what I heard before, provide modular and plug and play thermal energy storage solutions, optimize control. All this will enable full integration of thermal energy storages into the building or group of buildings and the network. And everything will be validated and should be, of course, scalable. In short, the impact, the KPIs, up to 120% increase in energy density, down to 50% reduction in investment costs, CapEx, of course, improved installation and simplified installation. And all this should make our thermal energy storage solution or solutions competitive with batteries. Of course, unlike batteries, we're storing electricity in form of heat or energy in form of heat. But in the end, what we are interested in is to be competitive on the market with alternative solutions such as batteries. And all this will be scaled up, as said, thanks to an aggregator system, which can be or should in the end be able to aggregate not only IoT devices, heating, cooling devices in the building, but even at a higher scale, so a group of buildings. We have four pilots. I think I'm already out of time, so I will jump quickly to the main solutions. This is our smart aggregator. It's a Swedish product, was developed for rather bigger energy demands, so larger case studies, and we will be testing it also on small scale, down to single buildings. This device, thanks to an advanced software, is not only able to, collect and understand data from IoT sensors, but also to make simulations in real time. And this belongs to the big family of edge ICT solutions, because the idea is that the computational capacity is not on the cloud. We still need a cloud to, collect data from the IoT, but also from the grid and talk to the smart aggregator. But the simulations, which require the main computational capacity, happen at the edge of the system. So in the building, let's say, or in the group of building inside the aggregator. And here you see, this is, let's say, a detail of what happens in the building. I mean, this gray rectangle, you see many different IoT devices, which the smart aggregator is capable of talking to and understanding, let's say. And all this will be connected to an open source platform with the aim of upscaling this and making possible to have many of these control systems, smart control systems, be aggregated together. That's it. I would like, first of all, to mention that we are also on social media. This is the LinkedIn profile, and we do also have, of course, a Twitter profile. And I also would like to mention that this is not directly linked to the project, but I think it's relevant for many of us who have talked today. There are many white papers being published all over Europe. Among those many, one is very recent on sector coupling. It's been developed, created, and published by two ETIPs, so European Technology and Innovation Platforms, one being RHC ETIP, where we or myself are members, so Renewable Heating and Cooling ETIP. The other one being ETIPSNet, so the ETIP for Smart Networks Energy Transition. So RHC is more on the thermal side, and ETIPSNet is more on the electricity side. Two different know-hows, two different worlds, which, and this is really the added value of this, trying now to talk to each other. Not easy, but the result is a very long white paper trying to focus on the main sector coupling assets we have in our energy system. And one, of course, is thermal energy storage. Emilia, it was 10 minutes.
You.
I think
yes.
I went through.
Thank you, and thank you for that tip. Unfortunately, we don't have time for questions now anymore. We would love to hear about this third project, European project. As you can all see, there are a lot of similarities, a lot of similar challenges, particularly this end user engagement, but there are also differences. So I would like to invite Ugo to please turn on your camera and let us know a little bit more about this BEST storage project. Ugo, you are an innovation project manager at Solienthal in Spain. So what's the specificity about BEST storage project?
Okay, yeah, thank you, Emilia. So good morning, everybody. My name's Hugo Grasset. I work for Solienthal. We're a small construction SME just around Madrid that also does energy efficiency refurbishments, and we are the coordinators for the BEST storage project. So what is BEST storage and what does it stand for? So if you go to the next slide, we actually have the acronym, which is Building Energy Efficient Systems Through Short and Long Spectrum Thermal Energy Storage. So to give a little bit more of context in the next slide, basically, in more detail, we have three sort of different storage concepts that are being developed. One longer term storage, which is a thermochemical thermal energy storage concept, one phase change material slurry storage, and then a vacuum insulated water storage. And the objective here basically is decoupling the power delivered and the energy stored to achieve modularity, and then from that modularity, you know, obviously get the cost savings, flexibility in design, size, and operation of systems for applications for residential applications mainly. So if we go to the next slide, I'm able to present our long-term thermochemical storage concept, which essentially uses excess energy from intermittent renewable sources, so PV, solar thermal, or wind, and then uses it later. The focus here is mainly on the coldest winter period, so for heating applications. What you have here in the actual scheme that you see here, a figure is the charging operation, so it's charged using excess energy at high temperature, so around 80 degrees Celsius, while heat is released at a temperature of about 20 to 30 degrees. And it can also be used to preheat domestic hot water applications. One of the important aspects as well is that the storage concept essentially works like a thermally driven absorption heat pump. And we use, we're very focused on cost effectiveness. So we're actually using absorbent or absorption material that is very cheap. And here it's lye. So we're looking at an inexpensive material that's around 80 cents per kilogram and is easily transportable and available. If you go to the next slide, we have the discharge operation of our TCM storage. On the left, you have the actual summer operation, so that the unit can be used for cooling as well, since it basically works as a thermal-driven heat pump. If you discharge the storage, heat can be removed from the building. But the main focus is obviously on winter operation, which you see on the right here. So the TCM is discharged to provide space heating using a low temperature store, either from either from the air or from solar thermal. And then also we have a low cost backup heating system within the systems that we're foreseeing. So if we go to the next slide, we have the general objectives. We're looking at at least a 4-week storage period. First, supplying space heating. And then in relation to current TCM storage designs, we want an improvement in 50% of heat and mass transfer. We want to reduce the vessel volume by 30%. And then we also want to increase the energy density by 50%, while reducing storage costs by 10% per kilowatt hour, which is essentially achieved by our cheap sorbent. If you go to the next slide, I'll present our PCM storage. So this shorter term storage, more focused on cooling. The PCM storage will act as a daily storage, allowing to cover peak cooling loads for a few hours, and then shifting electricity consumption to times where electricity is cheaper. So actually we have 2 philosophies that we're following here in our project. We are looking at, on one side, a PCM slurry system that's based around emulsion. So essentially the pump fluid has the phase change material that is dispersed within the heat carried fluid. And then we have another one that's PCM that undergoes supercooling and solidification in a controlled device called crystallizer. So both of these approaches will be developed during the project and tested with the development of the respective materials in both of these applications. If we go to the next slide, we have our third sort of storage concept, which is our vacuum insulated water storage, mainly for domestic hot water applications. Essentially here, it is a water storage with vacuum insulation. We will be connecting it to a heat pump as well as a solar thermal system and testing it that way. And a specific heat exchanger and control algorithms will be developed as well for this system. And here the sort of objectives or the KPIs that we're looking for is through vacuum insulation, we're looking at only having energy losses of only 2 to 3% of heat per day. And that is in contrast to the 20 to 80% loss per day for existing heat storage solutions on the market. And we're looking at having the ability to store heat for several days at temperatures of about 125 degrees Celsius. So if you go to the next, so our demonstration sites, we have 4 demonstration sites. One in Estonia, a single family home. We'll be testing the TCM and our vacuum insulated water storage there for heating and domestic hot water applications. One in Greece, it's a lab house. So we'll be testing the TCM and the vacuum insulated water storage for heating and cooling applications. One in Spain, it's the office building of one of our partners who's Techniker, and it's we'll be testing the phase change material slurry storage for cooling applications, especially for shifting cooling loads. And then finally in Switzerland, we have a single family house where we will be looking at the PCM slurry storage for heating and cooling applications in conjunction with the vacuum insulated water storage. If we go to the next slide, we are a consortium of 12 partners. We represent 6 countries: Spain, Switzerland, Greece, Netherlands, Germany, and Estonia. 2 of our partners are associated partners, given that they're in Switzerland, and one of them actually being our technical coordinator, which is Ost. And I think that would be it. I think I tried to squeeze it and make it as efficient and fast as possible. But if you want more information, we have our internet site, which you can see here. You can also get in touch with me directly. And we also have our social media channels, which you can find through our site.
Thank you very much. That was quite efficient. It's always the tricky part of being the last one to present. I would like to take this opportunity to ask all the speakers to turn on their cameras. We have 1 minute, so I have really quickly if you could summarize how, like your project, what is it that makes you unique? Because we heard a lot about the similarities. What do you think your project will bring to the table in the next 4 years? What's unique to your project? And Guillermo.
Thank you, Emilia. Well, actually, I think that this is a unique opportunity to focus on the thermal energy storage, not only in our project level, because as we have seen during these presentations, these 4 sister projects that conform this interesting cluster have several common objectives, several common technologies to be developed, but actually we have to think on the common outcomes also, because independently that we will work in similar technologies or with similar with similar thermal energy storages, the different outcomes that will come from different projects can serve to reach this decarbonization of the heating and cooling sector in Europe. No? So let's see how these 4 following challenging years works with these 4 projects, these sister projects, and how these the several activities that we can organize among this cluster can be shown to the whole European Union members. So.
And hopefully to the world. That was a little bit more than just a couple words. I would like to open the floor to Marco, Sara, and Ugo. If there one last thing you want to say, really short, about how your project stands out, please do.
Okay, I'll be starting, and there are many results, of course, but if I had to pick up one, then I would say stay at the higher level policy, let's say a lot of experience and new devices and systems and technologies to enhance sector coupling. Why? Because the world is going toward energy world towards electrification, and if we want our thermal assets to still be dominant in the market, we need sector coupling, in my opinion.
Yes, Sara, Hugo.
I'm happy to go. I think that one of the things that makes Best Storage stand out would be I think that Guillermo was talking about being user-focused earlier on to actually take the solutions to market. Best Storage has some pretty strict KPIs related to, or economic KPIs, especially in terms of the materials that are being used. And we also have a lot of tasks that are focused on the cost effectiveness of the system. So we're really trying to offer something that is economically interesting for our end users, and the development and technical developments within the project are very much focused around that as well.
Thank you. And Sara, what do you have to say about ECHO?
Yeah, I agree with all the contribution expressed by our partners, our colleagues. ECHO, of course, is funded in the same topic, so there are common challenges and there are common objectives, and for sure, I think that the most important ones are the socioeconomic impacts that this solution will achieve on the market and also on people, because the most important part of this project is well-being of end users and building owners. And of course, also environment, so mitigation of climate change, that is another very important aspect of the project.
Thank you very much. Thank you to all the speakers and all the listeners that took the time to be here today. I hope this was inspiring. And as I mentioned before, do follow us. We will follow up on this webinar with further developed in the coming 3.5 years.